I am recording this session right now, so and I have been posting the recordings. Have they been coming through okay out there?
Yeah.
Okay.
Also, would y minus z and z minus y be able to cancel out?
Y
Or what
minus,
or would it just be if they were the exact same?
yeah, it's the problem is if they took on the same value. If y and z, you put the same numbers in for y and z, and this is going to become 0, correct? And that is going to cause this denominator to 0 out.
I was saying that since you crossed out z minus y and y minus z,
Yeah.
so that does cancel out? Okay.
Yeah, the z minus y still drop out, and so we're still left with this reduced version here, okay? But again, because we get that potential hole structure in our graph, we still have to impose this restriction on y and z, that y cannot be equal to z. So,
Okay,
right.
thank you.
All right. Now this is a strange situation here. All right, trying to reduce this rational expression here. Of course, a restriction would state that this denominator can never be 0. So y minus x, if we set it equal to 0, we would get y is equal to x. So a restriction would be that y cannot be equal to x again. That would be the restriction we would have to impose on this, so it remains defined. But now, if we look at this rational expression here, we want to try to factor our numerator into our denominator. It doesn't look like we can really do any factoring with the numerator or the denominator here. Another thing is that it looks like the numerator and denominator are very similar to each other. It's just that the only difference is where the negative sign is. Here it's in front of the y, here it's in front of the x. Well, remember I indicated that you can always factor a -1 out of any polynomial at any time. Well, this would be the time and place to do so. So what I'm going to do is I'm going to factor a -1 out of my numerator. And when I do that, when you factor a -1 out of a polynomial, the effect is to leave behind the opposite of the polynomial you originally had. So you factor a -1 out of x, you leave behind negative x. You factor a -1 out of negative y, you leave behind plus y. Now, why did I factor -1 out? Well, because hopefully now we realize that negative x plus y is the same thing as y minus x. We spin these terms around. And so that we can see now that the y minus x is really reduced out to 1. And so this reduces down to -1, and that would be your answer. So I wanted to show you that because that does occur from time to time. All right. So in general, if you can remember this, you can take a shortcut. If you ever have a numerator and denominator that differ only by where the sign is, the negative sign is, it will always reduce down to -1, always. Okay. I want to show you that does occur from time to time. Now, I could have just as well factored a -1 out of the denominator and made it look like the numerator. You do not want to factor a -1 out of both the numerator and denominator, because if you do that, then you will have accomplished absolutely nothing. Okay, so that does reduce down to -1. Okay, another thing now is multiplying and dividing rational expressions. All right, so we're going to try to take 2a squared b minus ab squared. And this is going to sit over ab squared, 8b squared rather, plus ab. And we're going to take this rational expression and multiply it by a squared plus 16ab plus 64b squared. And this will sit over 2a squared plus 15ab minus 8b squared. So we're going to try to multiply these rational expressions together, and obviously we want our answer to be reduced. Okay. All right, so first of all, what we have to do is we have to factor all of our numerators and denominators completely. So what can I factor out of both these terms here? Anything? What would be the greatest common factor of both these terms? Looks like I can factor an a out and also a what? A b out, correct? So we can factor a, b out. And when we do that, we will leave behind 2a minus b. That's what we leave behind. Our denominator, can we factor it anyway? Does it? Well, all we can
B.
factor out is a B. Yeah, we can factor a B out, and when we do so, we leave behind 8B plus A. Okay, all those are completely factored. Now, can we factor this numerator of this second rational expression up here? Notice it is a trinomial construct here. There's nothing we can factor out of all three terms. It is a trinomial with a leading coefficient of 1. I need two factors of 64 that add up to 16, the middle coefficient. After some thought, I'm thinking 8 and 8, correct? So therefore, you know what? This trinomial factors. It is going to factor into A plus 8B times A plus 8B. That would be its factorization. So that trinomial is factored. Finally, downstairs, we have, unfortunately, a difficult trinomial to factor, one with the leading coefficient that is not 1. And to factor this, you know, you could utilize the grouping method or the trial and error method, whatever the case might be. So I can illustrate the grouping method. I'll take this downstairs and wrestle with it. So we start off by multiplying the leading coefficient and the constant. Well, in this case, it's not a constant term because we got b squared, but we'll multiply it by -8 here. So 2 times -8 is going to net me -16. And two factors of -16 that add up to 15 would be 16 and -1. Therefore, I'm now going to rewrite this as an equivalent 4-term polynomial. So I say 2a squared. I'm going to say plus 16ab minus 1ab minus 8b squared. And now I'm going to factor this 4-term polynomial by grouping. So we place parentheses around the first 2 terms. Got a minus sign that precedes the 3rd term, so I leave it outside the parentheses, which means I have to change the sign of my last term to avoid a sign mistake. Out of the first 2 terms, I can factor out a 2 and an A, and I would leave behind A plus 8B. Last 2 terms, I can factor out a B, leaving behind A plus 8B. Now we see we have a common binomial factor of A plus 8B that's shared between both these terms. Therefore, we can factor it out of both terms. There it is. Times, what would I leave behind in doing so? I'm going to leave behind 2A minus B. And that difficult trinomial has been factored. Let's bring the factorization back to our problem. All right, now the tough part of this problem is in our rear view mirror. All that remains is doing any reducing or cross canceling of like factors. Do we see anything that can be done here? Any like factors that can be reduced or cross canceled out? Anything?
2a minus b.
Yeah, this 2a minus b divides into itself once and divides into this 2a minus b down here once. That's valid cross canceling. Okay, anything else? Anything else?
A plus 8B.
Yeah, 8b plus a is the same thing as if you spin these around as a plus 8b. So these are identical. So these would cross reduce out, leaving you with ones. Anything? Oh, and we also have a plus 8b here and a plus 8b that reduce. Those reduce to 1. All right. Anything else? Anything else?
The b on the bottom and the b on AB.
That's right. These b's drop out. Okay. So this b divides into itself once, divides into b up here once. Heck, what am I left with? I have nothing but.
It's just a.
Just a over 1. Your answer is a. So this product reduces or simplifies down to just a. And we're done with that problem. Okay. So we multiplied those rational expressions together. After, of course, we did all of our reducing and cross canceling, and we're left with just a. So
I'm sorry.
What's that?
I'm sorry. The 2a minus b. Where did we get rid of that?
This 2a minus b here cross reduced out with this one down here.
Oh, okay. I didn't have that written down. Sorry.
This one went out with that one. Okay. Yeah, I mean, everything drops out except the lonely a left over when we get done. So that would be the simplified product of those two rational expressions. So what we're discovering, if nothing else, when we work with rational expressions, we have to know how to factor polynomials, because if we don't know how to factor polynomials, there's not going to be any success working with rational expressions. Okay, so that's why it's very important to strengthen that skill, your ability to factor various types of polynomials. All right, so if you're a little weak on that, continue to work on that. Try to strengthen the weakness, because you'll need that, especially if you go onwards and take more math after this course. Your ability to factor polynomials always comes back to haunt you. So try to continue to work on that. All right, any other questions about this problem here? All right, how would we divide some rational expressions? Well, in general, can anybody tell me how we divide fractions in general? Let's go way back to basic math and our thinking. Do you remember how?
Take the reciprocal.
All right, so we divide fractions by changing division to multiplication and flipping the second fraction upside down, or reciprocating the second fraction. We were taught that way back in basic math. And so now we're going to have to also do the same thing here, as we're being asked to divide some rational expressions. So the first thing we need to do, of course, is change division to multiplication and flip the second fraction upside down. And this is something that's easily forgotten, so be careful here. Change division to multiplication, and this guy has to now be flipped upside down. Okay, now that we've accomplished that task, we now have to do a whole bunch of factoring. We got to factor every one of these polynomials completely. So let's have an x cubed minus 64. What kind of a binomial are we confronted with here? How are we going to factor this?
It's the difference of cubes.
That's the difference between perfect cubes. 64 is 4 times 4 times 4, or is 4 cubed. Okay. Oh, but do we remember how to factor the difference of cubes? That's what's coming down to now. Do we remember that pattern, ladies and gentlemen? In general, if you got a cubed minus b cubed, you remember how the difference of cubes factors in general? A minus b times a squared plus ab plus b squared. So that's how the difference between cubes factors. That's a worthwhile pattern to memorize. Now, so therefore we got x cubed minus 64, and 64 being really what? 4 cubed. Do you agree? X cubed minus 64 is x cubed minus 4 cubed. So really our a is an x and our b is a 4. So wherever we see an a in this pattern, we drop in an x. Wherever we see a b, we replace it with a 4. So let's follow along here. So we got a minus b, which is to say x minus 4, times a squared, which is x squared, plus x times 4, which is 4x, plus 4 squared. But what's 4 squared at the end? 4 squared. It'll be 16. And there you go. This would be the complete factorization of this difference of cubes, x cubed minus 64. Let's bring that back and replace our numerator with its complete factored form. Okay, so that's how that factors. So therefore, I'm going to come back to my main problem and replace the numerator of the first rational expression with this factorization. All right, now in the denominator, how can we factor 16x minus x cubed? Well, what you can do is drag this off to the side of your paper and wrestle with it, and then bring its factorization back to the main problem. Notice I can factor an x out of both of these terms first, leaving behind 16 minus x squared. And hopefully we realize that 16 minus x squared, being the difference of squares, needs to be further factored down. So therefore, this further factors down into x times 4 minus x times 4 plus x. And this would be the complete factorization right here of 16x minus x cubed. Let's now bring this complete factorization back to our main problem and replace the denominator with it. So here we go. So that denominator is completely factored. And now we turn our attention to the numerator of the second rational expression. Fortunately, this is an easy type of trinomial, one that has a leading coefficient of 1. All I need, therefore, are a couple of factors of -8 that sum up to my middle coefficient of +2. And what would they be? Let's see. After some thought, maybe a little trial and error, who knows, maybe even using the calculator a little bit, we would get 4 and what? -2? As being the only factors of -8 that add up to 2. Being the case, this trinomial factors immediately into what two binomials? X plus 4 times x minus 2. And this trinomial now is completely factored. All that remains, ladies and gentlemen, is factoring a difficult type of trinomial here, but we are fortunate in some sense because we can factor a 2 out of all of each of the 3 terms. So that might help alleviate things. So therefore, let's first of all factor a 2 out of all 3 terms. There it is, and I'll leave behind in doing so x squared plus 4x plus 6. Now we're left with an easy type of trinomial to try to further factor down. To do so, I need 2 factors of 6 that sum up to 4. Do they exist? Well, the only factors of +6 are 1 and 6, 2 and 3, or -1, -6, and -2, -3. But none of these add up to +4. So this trinomial cannot be further factored down. Therefore, the complete factorization of this denominator is just going to be 2 times x squared plus 4x plus 6. Now that everything's completely factored, we can ask ourselves, can we do any reducing or cross-canceling? Any reducing or cross-canceling? Anything?
The 4 plus x and the x plus 4.
Yeah, 4 plus x is the same thing as x plus 4. So it will cross cancel out this x plus 4 up here. So they're gone. And when you cancel them out, you always leave behind factors of 1. Don't forget that. Hey, do you recognize something? X minus 4 over 4 minus x? What does this reduce down to? X minus 4 over 4 minus x. You remember that? What does this reduce down to? I think I illustrated this.
-1.
Yeah, it's going to reduce down to -1. All right, so this is going to drop out with this, but it's going to leave behind a factor of -1. So where are you going to put the -1? Well, you have to put it somewhere. So I'll just put it up in the numerator here, -1. Everybody see that there? This reduces with this and leaves behind a factor of -1. You could put it up in the numerator, the -1, or put it down in the denominator. It doesn't matter. It's got to be somewhere. Anything else? Anything else? These are not the same trinomial. Can't drop this 2 out with that 2. That's illegal. Well, okay, so that looks like about it. So what do we have left here? We got this -1 factor, which I'm just going to leave it outside of the rational expression. So put the negative sign outside. That accounts for that -1 factor in reducing these. All right, and in the numerator, we have what? X minus 2 times x squared plus 4x plus 16. And in our denominator, what we have left is just, we got this x here. Don't lose that. And we got a 2 and we got the trinomial. So we're going to have 2x times our trinomial of x squared plus 4x plus 6. And that would be it. You cannot do anything else. That is it. You cannot reduce anything else. So that is your final simplified quotient of having divided these rational expressions. Okay. So again, you got to do a lot of factoring. I mean, you got to know how to factor polynomials and all different types. Any questions about that one there? Okay, we're pulling in the 323. No. All right. I'm going to give you a classwork number 2 now. Let's see if you can do this second classwork. Call it classwork 2. I would like you to simplify both these here. So number 1, we got 2xy, and that sits over x squared y plus 3xy times x squared plus 6x plus 9 over 4x plus 12. Okay, you can do that one there. And then one last problem for classwork number 2. x cubed minus 8 over x squared minus 4 divided by 3x squared plus 6x plus 12 over x squared minus x minus 6. Okay, there you go. See if you can multiply and divide those rational expressions and get a simplified answer. Classwork 2. All right, anybody get number 1 reduced down? Feel confident?
I
No.
got 1/2.
1/2. Anybody else
I
get 1/2?
also got 1/2.
You got 1/2 too, okay.
Yeah.
All right, so let's take a look here. Factoring completely all numerators and denominators for number 1. That's all your how all your numerators and denominators factor. And then the x plus 3 drops out with an x plus 3. This x plus 3 reduces with this x plus 3. This xy drops out with this xy, and you're left with 2/4, which reduces down to, you are correct, 1/2. And that would be your final answer for that one. All right, number 2. Anybody want to share your answer for number 2?
X minus 3/3.
Okay, x minus 3/3.
I
Anybody
also
else?
agree.
Okay, let's take a look. Obviously, we have a lot of factoring to do here. This is the difference between perfect cubes, 8 being a perfect cube of 2. So it would factor into the product of this binomial and this trinomial. This is the difference between squares, factors into x minus 2 times x plus 2. This is an easy trinomial to factor, one with a leading coefficient of 1, 2 factors of -6 that add up to -1. Would be -3 and 2. So it factors like this. This one, the only thing we can do with this is factor a 3 out of all 3 terms, and then we just leave this behind that cannot be further factored, as there are no factors of 4 that add up to 2. Therefore, this trinomial cross cancels out here. The x minus 2 is reduced. The x plus 2 cross cancels out. We're left with x minus 3/3. And you are correct. And that would be your answer. So hopefully you did well on this, ladies and gentlemen, and this is making some sort of sense here. Okay. Any other questions about this classwork number 2 here? Okay, adding and subtracting rational expressions. Of course, in order to add or subtract fractions, we always need a common what? Must always have a common
Denominator.
denominator. And that was the case back in basic math. And that's certainly the case when you work with rational expressions also. Must have a common denominator. So this problem here, relatively speaking, is an easy problem because we already have a common denominator. So we don't have to fuss with that. Being the case, we just add our numerators together, m squared plus 6m plus 9 over m plus 3. And now we're back to about an hour ago. Can we reduce this rational expression? Well, let's try to factor our numerator, which is an easy type of trinomial to factor, which is quadratic in form, since this degree is twice the degree of the middle term. So I need a couple factors of 9 that sum up to 6. And 3 and 3, I think, fit the bill, correct? So therefore, this trinomial factors into identical binomials, namely m plus 3 and m plus 3. By the way, because this trinomial factors into the product of identical binomials, it's called a perfect square trinomial. We call this a perfect square trinomial because it's factorable into the square of a binomial. Okay. Downstairs, m plus 3 is factored completely. Nothing you can do with that. And the only other thing that remains now is dropping out one of these m plus 3 factors here. And we're left with the final answer of m plus 3. That would be your reduced sum of these two rational expressions. That was a pretty simple problem because we already had a common denominator. Okay. Pretty easy go of things there. All right. Now, obviously, you and I both know we're not always going to have that luxury of having a common denominator. Oftentimes, it's the case where we have to find a common denominator. And it certainly looks like it's going to be the case here if we're going to have any success in subtracting these two rational expressions here. So in order to subtract these rational expressions, first you want to make sure all your denominators are completely factored, and that does appear to be the case. Now we can put together easily our least common denominator. And what are we going to have in our least common denominator? In other words, what variable or polynomial expression do we need for our LCD such that it will be divisible by m minus 2 and m? Well, we're going to have a lone factor of m, and we're also going to have this binomial factor of m minus 2. So this would be the least common denominator of both of these denominators. Being the case, we're now going to build these fractions up into equivalent fractions where both denominators have to become the least common denominator. Notice this denominator has the m minus 2, but it's missing the factor of m. Because of that, we're going to have to multiply the numerator and denominator of the first rational expression by m to build our first rational expression up into an equivalent rational expression that now has the common denominator. The second rational expression, its denominator has the m, but it's missing the m minus 2. Because of that, top and bottom of the second rational expression must get multiplied by the m minus 2 to build it up into an equivalent rational expression with the common denominator. Any questions so far? Now that we have a common denominator, we can proceed to simplify our numerators more. So we have 4m minus 3 times m minus 2. And this all sits over our common denominator. Distributing the negative 3 inside the parentheses here, we're going to have 4m minus 3m plus 6 all over our least common denominator. Combining like terms in the numerator, 4m minus 3m nets us m, so we're going to be left with m plus 6 over m times m minus 2, and that would be it. That's your answer. There's nothing else you can do here. You can't do any reducing, and no more factoring, and that's it. So that would be your reduced difference of these two rational expressions. So for the first time we've seen where we had to get a common denominator, and then we had to build our fractions or rational expressions up into equivalent rational expressions that both have the common denominator. Any questions about that problem there? Okay, now just keep in mind before you put together a least common denominator, your denominator should be factored completely so that you can see clearly what factor or factors you need for your LCD. If your denominators are not factored, that requirement will usually be obscured and you won't be able to see clearly what you need. Okay, all right, any other questions about these problems here? All right, let's get rid of that there. Get rid of this here. Try another one. Okay, so let's try this one here. Let's try to subtract 1 over x squared plus xy minus this rational expression of 2 over x squared minus y squared. So we're going to try to subtract these two rational expressions. Notice we do not have a common denominator, so that's something that we're going to have to address. Before we can find a common denominator, we're going to have to make sure all of our denominators are completely factored, however. So first, we must factor our polynomials. What can I factor out of both these terms here? I can factor out an x, and I'll leave behind an x plus y. Here I have the difference between perfect squares, or two squares, so I can factor this as x plus y times x minus y. Okay, so what do you think our least common denominator is going to need now? What are we going to need for our least common denominator? We're going to need an x, a lonely x, and we're going to need also what? An x plus y. And we're going to need an x what? Minus y. You are looking at your common denominator. So your common denominator is x times x plus y times x minus y. Being the case, we now need to build these rational expressions up into equivalent rational expressions that both take on the common denominator. The first one's got the x, it also has the x plus y. It's got the x and x plus y, it's missing the x minus y. So top and bottom of this first rational expression has to get multiplied by x minus y. That builds this first one up into an equivalent rational expression with the common denominator. The second rational expression has the x plus y and the x minus y. It's missing just a factor of x. So we have to multiply the numerator and denominator of it by x. And that builds the second rational expression up into an equivalent rational expression now with the common denominator. Now that we have a common denominator, we're in business. We can begin to simplify our numerator. We got x minus y minus 2x, and this all sits over our common denominator. The numerator, combining some like terms here, we got 1x minus 2x gives us negative x over our common denominator. Now, can I factor my numerator in any way? Because you got to entertain that possibility, so that if you can, you need to see if you can do any reducing. How would I factor my numerator?
Could you do x minus y cancel out?
Well, negative x minus y is not the same as x minus y. Okay, because you got a negative sign in front of x. But what can I factor out of both these terms here first?
Would it be a -1?
Yeah, we can factor a -1 out. Just take the -1 out. We leave behind x plus y. Oh no, that looks good. Because now we can see that that x plus y in the numerator is going to drop out with the x minus y factor in the denominator. Correct? So now we can drop the x plus y's out. Looks like my final answer is going to be -1 over what? X times x minus y. And that is it. That's about all you can do with that problem there. You know, again, you could put the negative sign outside of your rational expression. It doesn't really, when you have a negative fraction, it doesn't matter where you put the negative sign, whether you attach it to the numerator, whether you attach it to the denominator, or whether you just leave it outside of your fraction. These are all equivalent to each other. Agree? Okay, so there you go. You can express it like this, or your final answer like this. Make sense? Or if you feel extra courageous, you could even distribute this -1 inside the parentheses here and call your final answer 1 over x times y minus x. That would also be equivalent if you wanted to do that. I mean, you know, I don't see really any reason why to do that, but this technically is equal to this, which is equal to this. Okay, they're all equivalent to each other. All right, questions about that one? But again, you could just leave it like this or this. You don't have to take the -1 inside the x minus y down here. You can if you want, but it's not necessary. So I'm going to just leave it like that. All right, any questions about this problem here? So we're adding and subtracting rational expressions by, of course, getting a common denominator. And then going from there. Okay. All right, classwork number 3. Classwork 3, let's see if you can simplify these. Number 1, 7 over 4a, plus 11 over 10a squared. See if you can do that one there. And we'll give you another one here, 3x plus 5. Well, actually, I don't think I'm gonna have enough room there, so I better write the second one down here. And number 2 should be 3x plus 5. And that'll sit over x squared plus 4x plus 3 minus x minus 5. And that's going to sit over x squared plus 2x minus 3. All right, so see if you can add and subtract these rational expressions. We'll call that classwork number 3. Well, which problem is easier, 1 or 2?
1.
That's an understatement. Yeah, number 1's 10 times easier than the second one. Did anybody get the first one? Feel pretty confident about that? That one's pretty reasonable, not too bad.
35a plus 22 over 20a squared.
Over 20a squared. Okay. Anybody else get that?
Yeah.
All right, that sounds good. So number 1 is pretty, relatively speaking, not that bad. Common denominator of 4a and 10a squared is going to be 40a squared. And so we're going to have to, multiply these rational expressions by appropriate factors to build them up into an equivalent rational expressions with the common denominator. And then once you get a common denominator, then you proceed to work with your numerator. You factor a 2 out of both these terms here, and then that 2 will reduce with the 40a squared and down to 20a squared. And that'd be the final answer there.
You could have did that with 20, right?
What's that?
I used 20 as the least common denominator.
Yeah, I did too.
Ooh, yeah,
Then we'll-
yeah. Yes, you could. Wow. Yeah, I do not have the least common denominator. I have a common multiple or common denominator, but it's not the least common denominator. Yeah, actually, the least common denominator should be 20a squared. You are correct. So the downside of me using 40a squared as opposed to 20a squared, which I probably should have used, is I had to do a little reducing in the end. Do you agree? That's the extra overhead I incur in using 20a squared as opposed to 40a squared. But nonetheless, we end up with the same answer in the end, so we're both good. Okay. All right. The next problem is a long problem. For one thing, you're going to have to factor your trinomial denominators here, and you need to do that to determine what you need for your least common denominator. And you are going to need an x plus 3, an x minus 1, and x plus 1 for your least common denominator. First denominator has the x plus 3 and x plus 1. It's missing the x minus 1. So you're going to multiply top and bottom of the first rational expression by x minus 1. Second rational expression has the x plus 3 and the x minus 1. It's missing the x plus 1. So we multiply top and bottom of the second one by x plus 1. Then we've got a bunch of multiplying to do here. You got to FOIL out these binomials, FOIL these out here. Now, when you FOIL out the last two, you got to make sure that you're subtracting that entire expansion or product. So make sure you enclose this product inside parentheses here that precedes this minus sign. That's very important there, okay? And what you do after that, then you're going to gather together like terms, and then you go from here to here. Notice, instead of writing my least common denominator over and over and over and over again as I strive to simplify my numerator, why not just say this is over the LCD and we'll bring it back when we need it, okay? So I go from here to here, and then here to here, and then I combine like terms, my 5s drop out. And then I'm left with this, and I can factor a 2x out of both these terms here, leaving this behind. And finally, the x plus 3s drop out, and I'm left with this final answer. Did anybody get this final result here? Down here?
I was kind of stumped halfway through.
Yeah, I'm still working on it. I was waiting for that
Quite a
answer.
problem. Yeah, it's a long problem. There's a lot of room for error on this problem, okay? So, you really just have to practice some vigilance here and perseverance. But it's a lengthy problem. Yeah, but that's what I did get down here for the final result. So if you want to take a picture of that or whatever, go ahead for your own purposes. You can go ahead and take a picture of that. All right, so that's classwork number 3. All right, we just have a couple more problems to do. We'll wrap this up here. We're going to look at a couple of problems that involve some radicals, some negative exponents, and a complex fraction or two. And we'll wrap it up for today, okay? All right, let me know when I can move onward. Are we good on this last one here, or?
I'm good.
All right, anybody else still need it up here? This problem, this last problem. All right. Okay. Well, let's wrap it up. All right, so let's see if we can simplify this radical expression here. we have 3 times the cube, 3 times the square root of 3 plus the square root of 6, and all this is going to sit over 5 times the square root of 3 minus 2 times the square root of 6. Okay, so we're going to try to simplify this radical expression involving these square roots. And we have some work to do because we have square roots appearing in the denominator of this fraction. And that's one of our no-nos, one of our 3 no-nos we learned in the past. Never leave any radical appearing in the denominator of a fraction. It's not considered to be simplified. And so the only way we're going to get rid of these square roots in our denominator is we're going to have to multiply the top and bottom of this entire construct by the conjugate of the denominator. And what would be the conjugate of this denominator? The conjugate of this denominator.
You just add it.
So it'll be 5 times the square root of 3 plus 2 times the square root of 6 is what we're going to have to multiply the denominator and the numerator of this thing by in order to rationalize the denominator. So that's what we're going to have to do. In order to knock out these square roots in our denominator, we're going to have to multiply top and bottom of this thing by the conjugate of the denominator, which is this. All right. All right, now in the numerator, we're going to have to kind of employ our Boyle algorithm that is used to multiply binomials together. Technically, these are not binomials, but we can still use the algorithm in order to expand out their product. Okay. Now, in the denominator, life is good because we have conjugates, and we learned ways back that when you multiply conjugates together, you're always going to get the difference between the what? The squared terms, correct? That's how conjugates always play out in their multiplication. And so therefore, it's a very simple thing to multiply these conjugates together. All we have to do is square the first term. Put a minus sign and square the last term. And that would be the product of the conjugate denominators. In the numerator, we're not so lucky. We have to multiply this all out. So what's 3 square root of 3 times 5 square root of 3? Hopefully I can omit a subtle step in here. What's 3 times 5? That's 15. And what's the square root of 3 times itself? That will be the square root of 9, but the square root of 9 simplifies down to 3. So 3 square root of 3 times 5 square root of 3 is going to be 15 times 3. Plus, multiplying the outer terms together, 3 square root of 3 times 2 square root of 6, 3 times 2 is 6. And the square root of 3 times the square root of 6 is the square root of 18. Plus, now we can multiply the inner terms together. Square root of 6 times 5 square root of 3 is going to give us 5 square root of 18. Finally, the last terms, we have square root of 6 times 1 square root of 6 times 2 square root of 6. That's going to be 2. And what's the square root of 6 times the square root of 6? That's the square root of 36, which is just 6. So 1 square root of 6 times 2 square root of 6 is going to be 2 times 6. And this is all going to sit over the square of 5 square root of 3. That means we got to square the 5, which is 25. And when you square the square root of 3, this just becomes 3. The square of 2 square root of 6 is going to be 2 squared, which is 4. And the square of the square root of 6 is 6. All right, so 15 times 3 is 45. These are like radicals. These combine. So 6 square root of 18 plus 5 square root of 18 is 11 square root of 18. Plus 12 at the end. And this sits over 25 times 3, which is 75, minus 24. Further simplification, 45 plus 12 adds up to give us 57. Now, 18 is not a perfect square. However, 18 is harboring a perfect square of 9. Square root of 18 being the square root of 9 times 2. So the square root of 9 brings a 9 out as a 3. That 3 gets multiplied by the 11, turning it into a 33. Times the square root of a 2 will remain. Downstairs, 75 minus 24 is going to net us 51. All right. Anything else we can do here or should do? with a little bit more inspection and thought in the numerator, we can factor a 3 out of both these terms in the numerator, I believe. 5 plus 7 is 12. 3 divides into 12, so 3 will divide into 57. That's the 3's divisibility test. So 3 times what gives us 57? 19. And 3 divides into 33 11 times. Now, why did I factor the 3 out? Because I believe 3 over 51 reduces. 5 plus 1 is 6. 3 divides into 6, so 3 will divide into 51. 3 divides into itself once, goes into 51. How many times? 17 times. Final answer. 19 plus 11 square root of 2 over 17. And that's called simplified. Okay. It's simplified because we no longer have a perfect square underneath the square root. We don't have a square root appearing in our denominator, and we don't have any fraction underneath our square root. So we're good. That's your final answer. Questions how we did that problem there? All right,
I have a question.
Yes.
So how'd you get 33?
Back here, 33. The square root of 18 is going to be the square root of 9 times 2, which is 3 square root of 2. And that 3 got multiplied by the 11 out here. You see that? 11 times 3 is 33, square root of 2. So square root of 18, I brought the 9 out as a 3 and then multiplied it by the 11. And I got 33 root 2. Do you see it?
Yep.
Okay, any other questions? All right. So if nothing else, a lengthy problem. And I know if I was doing a quiz or homework or an exam on Alex, I would definitely have a pad of paper handy and something to write with. Try not to muscle these out in your mind, ladies and gentlemen. I mean, if you can muscle this out in your mind, you have a skill that I just don't have. You got to let me know how you do it. Okay. All right. Any other questions about this? All right, let's look at maybe a couple of other miscellaneous problems here to wrap this section up. The next one is going to be trying to simplify 3u to the negative 1 power minus v to the negative 1 power over 9u to the negative 2 power minus v to the negative 2 power. So we're going to try to simplify this expression. The reason why it's not simplified is because we have negative exponents appearing everywhere, and we got to get rid of these negative exponents. So the first thing we'll do is address the negative exponents. Of course, u to the negative 1 power can be rewritten as 1 over u. So 3 times u to the negative 1 power can be rewritten as 3 over u to the first power. V to the negative 1 power, it can be rewritten as 1 over v using our definition of negative exponent. 9 times u to the negative 2 power is 9 times 9 over u squared. And v to the negative 2 power is really going to be 1 over v squared. What we got going on here is called a complex fraction. Whenever you have fractions over fractions, you have a complex fraction, and they are a mess. And so for that reason, we would like to simplify this complex fraction all the way down to a simple, ordinary, reduced fraction. The quickest, most efficient way to do that, this is not the only way, but it is probably the most efficient way, is to first of all identify what our least common denominator would be for all of our denominators. And what do you think our LCD would be for u, v, u squared, and v squared? Anybody? What do we need for our least common denominator? Of all
Would
those
it be
denominators.
uv squared?
Oh,
So u
it's
squared,
gonna,
v squared?
yeah, it's gonna be, well, it's gonna be u squared, v squared, exactly. We're gonna need a u squared and also a v squared. That is your least common denominator of all of these denominators. Now, here's what we're going to do. To simplify this down to an ordinary simple fraction, I'm going to take this entire thing, and I'm going to multiply the top and bottom of it by the least common denominator. So I'm going to multiply the numerator by u squared v squared, and I'm going to multiply the denominator by u squared v squared. This is the quickest way to simplify a complex fraction. This u squared v squared, which sits over 1 here, is going to have to be distributed into both these terms here, this term and this term. So therefore, this 3 over u here is going to have to get multiplied by u squared v squared over 1. Minus 1 over v has to get multiplied by u squared v squared. Our denominator is also going to get multiplied by this u squared v squared. So this u squared v squared is going to distribute into both these terms here in our denominator. So we're going to have 9 over u squared and that's got to get multiplied by u squared v squared over 1. Minus 1 over v squared has to get multiplied by u squared v squared over 1. Now that we've done that, we can now see through cross canceling how we're going to eliminate all of these fractions here. What can I reduce here? Cross reduce. This u will cross reduce out with one of these u's. Do you agree? So this u disappears, divides into itself once, and divides into u squared here, u times. Because of that, I'm left with 3 times u times v squared, which is 3uv squared. Minus, notice this v will cross reduce into this v squared here. So this v divides into itself once, divides into v squared up here, v times. Then I'm left with 1 times u squared times v, which I'm going to report it as u squared v. Fraction gone. Downstairs, this u squared cross reduces well with this u squared, leaving us with 9 times v squared. Fraction gone. Here the v squareds cross reduce out, leaving us with 1 times u squared or u squared. Well, look at that. We got rid of all of our fractions in the numerator and denominator. Now it's just a matter of reducing this rational expression. Any questions how I got it down to this? Right here. All right, onward we go. Now, to reduce this rational expression, we have to ask ourselves, can we factor our numerator and denominator? Notice we can factor out a u and also a v out of both these terms in the numerator. And when we factor uv out, what do we leave behind? 3v minus u, right? How can I factor the denominator down here? Well, there's nothing we can factor out of both these terms, but this is the difference between squares. So it factors into 3v minus u times 3v plus u. Finally, we can reduce out the 3v minus u's between the numerator and denominator. We're looking at our final answer, which is uv over 3v plus u. And there's your final simplified result for that problem. So we started out with a very nasty situation with a whole bunch of negative exponents. We rewrote it to get rid of the negative exponents. We then seen that we had a complex fraction to simplify. We multiplied top and bottom of it by the least common denominator, eliminated all our fractions, and then we're back to reducing a rational expression. Factoring the top and bottom leads to this final reduced result. Any questions how we tackled that problem? Okay. Yeah, usually the most difficult part of the calculus, ladies and gentlemen, is dealing with the algebra. The algebra and calculus can be at times somewhat challenging, not all the time, but at times it can be very involved and lengthy too. And for that reason, it's wise to have gone through college algebra here before you go onwards. Okay. And like I said, if Alex is not challenging you enough with problems, please do, by all means, go into your textbook and not only look at the examples in each section, but try to do some of the odd and even problems at the end. I'll provide you with all the solutions to all those problems. It's a wealth of extra practice just waiting for you there, okay? I know if I needed extra practice, I would definitely go into my textbook and try to do as many problems as I could possibly fit into my schedule. All right, any other questions about this? All right. Now we will look at how to simplify one like this. And this becomes important, usually in Calculus 1, when you're working with limits. You oftentimes run into complex fractions of which you have to try to simplify. And so hence the algebra, okay? All right, ladies, we're going to try to simplify this expression. We got 3 over 1 plus h minus 3, and technically this 3 could be placed over 1, no harm done, over h, and this h is technically over 1 also. All right, what we got going on here is we have kind of like a fraction in our numerator of an entire fractional construct. I don't like that. This is kind of like a complex fraction here. And in order to simplify it down to an ordinary fraction, I'm going to multiply top and bottom of this thing by the least common denominator of 1 plus h, because that is the least common denominator, 1 plus h, 1 and 1. It's 1 plus h. So let's do that. Let's take this entire complex fraction, multiply top and bottom by 1 plus h. Notice, because we're multiplying the top and bottom by 1 plus h, we're really multiplying this complex fraction by 1. This is another way of expressing 1. Anything times 1 is still going to be equivalent to itself. Okay, hence the equal sign. All right, this 1 plus h gets distributed into this term and this term. And so this is an optional step here. When you get good at this, you can usually omit this step, although I am going to include it for now. And this 1 plus h gets multiplied by my denominator down here also. All right, so that's what we're up against here. When I multiply these fractions together, what cross reduces out here? The 1 plus h's dive out to 1, leaving me with 3. Here we have minus 3 times quantity 1 plus h. Downstairs we have h times 1 plus h. Okay. Distributing the negative 3 inside the parentheses here, we're going to have 3 minus 3h all over h times quantity 1 plus h. Whoops. These 3's drop out here, leaving you with negative 3h over h times 1 plus h. And notice we can reduce this h with this h here because they're both factors. So the h's drop out, leaving you with your final result of negative 3 over 1 plus h, and we are done. Okay. So that's your final result for that one. There you go. All right. Everybody see that there? All right. One last problem, ladies. I'm only going to give you one problem for classwork 4, okay? Just one, and this will close the door on the session. One problem. I would like you to try to simplify this. Classwork, I believe we're up to number 4. Let's try to take 7 over x plus h minus 7 over x, and all this is going to sit over h. See if you can simplify that expression, okay? And again, this is a typical situation you run into. Usually your first semester of calculus, when you're working with limits, oftentimes you run into nasty complex fractions that need to be simplified, okay? So there you go, try to simplify that. Did anybody get it?
I was still writing when you started.
All right, I'm gonna leave that up there, okay? So if you want to hang on, ladies and gentlemen, I'll hang on the line for a couple minutes. If you have any questions, I'll leave this on up there, up here for a couple minutes so you can look it over. But if you don't have any questions, you have a great weekend, and I'll open up the chapter R quiz on Alex, okay? And that's due by October 3rd, midnight, all right? And I'll also open up and update the extra homework that we need to open up, having done this today. All right, so there we go.